Hey everybody, it's Christine and welcome back to the fourth installment of Electrobiology. Alright, so usually I do some disclaimers and stuff, but I'm going to keep that in the video, so I'll spare you all of that. So if you're ready for some science and biology theory, sit back, relax, take your troubles to the door, and do that stuff with me. Alright, let's go. So the last time we left off at the generative principle. Now, what may that entail? Well, obviously it will entail some magnetism. And so what is magnetism? So simple. It's just attraction and repulsion. That's the simple definition of it. So how do we get to magnetism? Well, we have to do a couple things. We have to talk about the current and ether. Okay, so what is a current? It's just a disruption of the ether. Okay, now let's get to ether. Now what the heck is ether? Well, basically ether is just a matrix, medium, substance, something to work on or act upon. So just maybe some examples might be the atmosphere, space, water. In my old working life, I used gel for both growing plants and like PCR, like gel electrophoresis, that kind of stuff. And even then we would run a current through that to get certain information. So anyway, that is what ether is. So now that we've been introduced to a current as it relates to the ether, now the current can also be used in different terms. So you can also say a current can occur as a flow or a flux. And in this case, a laminar flow, that is just a undisrupted current, basically. And then also it can be ordered, and then it can go into a disordered state. So a disordered state would be a turbulent flow or a turbulent flux. And then as it goes from an ordered to a disordered, it's going to disrupt that ether. And we'll go over these wells a little bit later. But so if you want to look up the Thunderbolts project, they have wonderful information. And they also have something called the Z-pinch theory. So we'll go over that a little bit later. Before we bring some concepts together, I'll just do my first disclaimer. So there are many theories on everything, including particle physics and the ether and how you get to particles and atoms and this and that. The current theory, the popular theory that is out there in particle physics, me personally, I just don't understand it. I don't understand the dynamics. I do understand that I believe there is about 16 particles, and some they can't really explain how they appear or disappear. Some of them are broken up into 3 different charged particles, like in one particle, so say that 2 are possibly negative and 1 is positive, but they never really explain how they get to a charged particle, or they never explain what it is. What is positive and what is negative. So with that being said, I did run across a paper, and it's the best one that I have read so far, and the paper is called Fundamentals of a Theory of Ether, and it's by Lori Gardy and Linnell Deneau. So that paper was written together, and they each have their own YouTube videos on it. So I'll link all 3, the paper and both of their videos. They're very enlightening and very, they explain it very well. So I do encourage you to read it and watch the videos. Okay, now with that being said, I say there's 2 ways of achieving attraction. So again, what is attraction? It's just bringing things together. So you can explain it in 2 ways, but they really go through one way in their paper. So if I step outside of their study, it's just me trying to explain it to myself, and is if I'm explaining it to someone else. Alright, so let's get in with the meat of the issue. So in their experiment, they ran a current through water. Now they had some canisters set up. So as they were running this current through the water, it would go and it would spin a canister. So upon the spinning, So this is going to be the same canister. So it would spin and spin, and eventually the inertia, remember that word? The inertia is, if it wants to be at rest, it's going to tend to stay at rest, and if it's not at rest, it's going to want to keep on moving. So that is actually what it's going to achieve. So as this is moving with the current, it's eventually, the inertia is eventually going to be pushed down. Now, inertia is going to go all over the place, but in this instance, it's going to go down. And if we just erase this little top section there, and we're just going to go with the bottom, they had set up a second canister. So now it is spinning here. It's going to go down, and it's going to start spinning this second canister here. So what was that net effect? Well, the net effect was going to be, if they ran a current, the current was going to spin a canister, and one direction would go this way, and as they would spin a canister, that second canister, so it would go up, down, around. Remember that figure 8 from the first video? It would come down, and then it would shoot out this way. So they are going to be equal and opposite directions. So this is going to have a spin going this way, and this one's going to have a spin going this way. So the result of that is going to be, as the current is going through, I know it's going to be hard to see this on my diagram. So there's going to be a current going through and a back current on both of these. Because you have to remember, this is going to go this way also. And this is going to go this way. And if you complete that cycle, some of that inertia is going to go forward, and that part is going to go forward as well. The second way they got that spin, or I'm thinking it wasn't in their paper, so you could push a current and just both of these canisters or cylinders would spin at the same time. So where might we see these patterns in real life? Well, they do experiments with aviation to see what kind of the least turbulence there can be for your aircraft. So here we go. Here's a little obstruction here, and this is probably just some kind of a smoke to highlight the current. So anyway, this is going along, and these obstructions are going to cause these turbulence patterns here. So it doesn't necessarily have to be a canister. It's just going to naturally stir up that air, and you see those beautiful swirl patterns. And here's an airplane coming in for a landing, and again it's producing those beautiful swirl patterns as it disrupts the ether or the air. Let's scale this up quite a bit. This is the schematic of the Earth, and as it's turning on its axis, it's going to create a current. So this being the widest part, the current is going to force this air to go around with it. So, and then it's going to make those beautiful turbulence patterns, and eventually that inertia is going to spin in another direction. So one direction is going to go this way, and another, because of that spin and the angle, it's going to turn to spin this way, and again it's going to turn and spin this way. So this and this will be parallel to each other, and this will be parallel to each other too. Pretty important for international travel, and if you want to go through this without too much turbulence. Let's scale this up one more time to the beautiful striped planet of Jupiter, and here you can clearly see the current system. So I know it's kind of opposite of what it might appear like, but there are two currents going here, and what we were talking about, the backflow, is here. Here is one more representation of the stripes and the turbulence patterns as well. You can see that it's just so gorgeous, and it's starting to make those swirl patterns there. So now that we see some of the flow patterns associated with the current, now let's see what we can do with it and how it is related to attraction. And that's my cat right there. So let's follow the current there. It's going to create those beautiful swirl patterns, and then what it's going to do, if we keep with the same system, so it's going to turn these canisters, or however you want to think about it. It's going to push that, the inertia is going to follow it up, and then it's going to come back down, same as the underside. So it's going to push, and the inertia is going to come, and it's going to meet here. Top and bottom are going to meet, and then they are going to clash. So as you can see, that's going to open this part up. It's going to force this to go down and this to go up. Now this is the attraction. It's this coming down and this coming up. Same thing, we're going to keep on following it. As soon as it goes through, this is going to also push this up. And so this pushing up part here is going to push these sections, this section down and this section up. Now both of these, if I can get these in the picture here. So now both of these, this point and this point, is attraction. So now this dynamic is going to weeble wobble until it can equalize both top and bottom as the current is going through. So again, this is just going to be a review. So the current is going to go through, this is going to go up and down. So this is going from the bottom one, this is going to go down and up. So together, when they equalize in proportion to the current, it's almost going to act as a square knot, as if they're going to close the gap here. Okay, so now that we have this according to the current, let's go into a traditional way of how attraction is defined. So okay, so there's many examples on videos and things of currents through two wires. Alright, so this is going to be one system, just like the system that we had talked about earlier, but now there's going to be two systems. There's going to be two currents running in the same direction. So we're just going to follow that pattern one more time. This is the same system as up here. So the top is going to go around and down. The bottom is going to go around and up, which the bottom system of here, we're just going to take that here. So there you go. And then now let's take the second system. So it's going to be the same as the top. So around and down, and the bottom system is going to go down and up. Now with this one, we're just going to take the top. So this system we're taking the bottom, this system we're taking the top, and so it's going to make that same dynamic, just as if you were working with that original system up here. It's just working with the back current. So this is going to have that same dynamic and that attraction as one system, where the back current is actually the attractive force between two currents. Now let's take a look at repulsion. So what is repulsion? So it's basically if you take two systems but run the current in opposite directions. So one is going to go this direction and the other one's going to run in this direction. We're going to run in the same pattern of disruption of the ether. So basically how we were saying that this one's going to go around and down, and this one's going to go around and up, and in this one now it's flip-flop, so we're going to do it the opposite way. So we're going to go, the top now is going to go around and down, and now this one is going to go around and up. So now let's look at the down section and the up section here. Now these are going to be traveling in the same direction. It's going to be running in the same direction here. So what does that mean? So okay, so when we go around and down, now when we take the bottom and we go around and up, that means they're almost going to be hitting a wall. They're going to be clashing and bouncing off of each other. There's nowhere to go. It's not going to be working together as like attraction. Attraction has that working together with a back current. There's no back current here. There's only clashing and just bouncing off, basically. And that bouncing off is the repulsion. There's nowhere to go. See how it's going to clash and it's going to bounce. That bouncing is that repulsion. Alright, I pulled out some high-tech equipment. Here's some tuna cans, and later on you're going to see some pinwheels from my daughter. But anyway, let's do a little bit of a review. So we have the current here, and then pretend this string is going to be the inertia. So in the experiment, the inertia is going to come around. It's going to start twisting that canister. It's going to come down and around. It's going to start spinning a second canister here. It's going to keep on going. Now remember, this is going to start to weeble wobble until it's going to equalize. So there's going to be a little bit of attraction here. See, did you see that? That little bit of attraction, and now they're going to start working together. So it doesn't really matter what direction it's going to move in. And actually this is kind of working like that first picture that the swirls were a little bit offset. Here's that second way where the inertia just came. Here's the current that runs through. The string is going to represent the inertia. The inertia is going to go up and around and shoot out again. So let's do that. So you're going to see a little bit of an attraction here. These are just going to pull together, and now now the pressure is equalized, and now they're going to start rolling together. Okay, let's do it a little bit faster so you can see that effect. Alright, there you go. Okay, so let's just work with some pinwheels. So that first experiment was going to have the current go down, and the inertia was going to spin that one of those canisters around, and then it's going to do that figure 8. It's going to make that other one spin. The second way was if we just push, that current would just push that inertia together. So let's just do that. So as you can see, both of them are going in this direction. That's forcing that to go this direction, and then there's going to be a back current going there. So now let's do a little bit of repulsion. Repulsion is going to be two systems going in the same direction. So this one's going to go in this direction, and this we're going to spin it the same direction. So you can kind of see there where they're going to smash up, and they're going to slow each other down if they don't careen into each other and bounce off. This one was a little bit shorter, as you can see, whereas the attraction would work together. Okay, let's try this with real magnets now. So I just have one named north and one south, but it's really just the direction of a current or a system. So I have this arrow pointing this way. So this system is going to go this way. And then I have the south, and then this system is going to go this way. So basically what they're going to do is they're going to come around and meet and get sucked together as when they're forming the back current. So let's give this a try. So remember, these are going to get sucked together, then they form a new back current. Oops. Wasn't necessarily supposed to happen like that. Hang on a sec. There we go. There we go. Okay, so now I'm just flipping that over, and then now I'm just going to keep the south, and now this current, this system is going to go in the same direction. So here we go. We're going to point this, and we're going to go like this. This is now going to be the direction of this, and then this is going to be the direction of this. So now when they come, they're going to be clashing and bouncing off each other. So clashing and bouncing off of each other. Okay, now let's give this a try. See, it doesn't really want to do anything until, there we go. That back current is so strong. There we go. Now let's move in the opposite direction. There you go. So now that we have some ideas about the current and the disruptive patterns it has on the ether, now let's explore some of these disruptive patterns as it relates to an electromagnetic field. Now I know this says electricity right here, but we'll visit that in a little bit. So let's go back a few pages in the notebook. So we have that, we have the current here and a disruption pattern here, but instead of going across the current, let's just imagine and let's just stick with the top pattern. You can do it with the bottom one as well, but just to have a direction, or just to say something that is superior, let's say, instead of inferior being the bottom. So let's just follow this pattern here, and just let it keep on going. So now it won't necessarily just be in succession like that. So let's go back to our page here. So like I said, depending on your the way that you're looking at it, it doesn't matter if it's this is just going to be a superior aspect and this is going to be an inferior aspect. So I'm just going to label that north and south for the moment. If we were to follow the current, that would be a much different story. But for right now, the labels actually don't matter. So, all right, so let's go back to these swirl patterns, but they're not just going to line up like that. They're going to basically layer right on top of each other. And I'm bringing my little example back from video 1, if you guys remember that one. So basically, this is going to represent the empty part of the swirl pattern. So just that little part right in the middle of it there. So because if you try to twist a rope around nothing, the knots are just going to fall apart. That's all. So anyway, it's going to twist, and those are those swirl patterns there. And now they're going to kind of layer on top of each other. Now this layering and crossing is going to develop a backbone, as you can see there. Eventually it's going to twist around the current. The current is actually going this way. I don't know if you can imagine that. So maybe I'll go down here just a little bit. And the current is actually going to lay in the middle of that. Oops. So just like that. So I apologize if the single helix and the current wasn't very clear, but what I did now is if you take the superior aspect and the inferior aspect and you put them together, I'm going to go back to that example that I had in video 1, and here's that beautiful example of the double helix. Now if this pencil is the current, it's going to run in the middle of that pattern. So here is the one helix here. It's going to go down and over in this way. The other one is going to go in the opposite direction. It's going to cross over and underneath and come back up here. Remember, in the first video we were talking about X marks the spot. Here's another beautiful example of a double helix. Now this is basically a fancy hairpin that's used to secure your hairstyles, but like I said, it also does have the shape of a double helix. Now I don't know if you can see that, but I'm just going to twist this a little bit, and I'm just going to give you some little mythologies as we go along. So if you're going into the myth side, maybe you could explain this with the nagas or snake heads. Now as I twist it, it's going to have the appearance of ascending. Okay, I'm going to stop right there. Another very, very old idea from ancient Egypt is that they more or less saw time as a coil, and this is where actually I got interested in the shapes and some of the explanations. So just a little bit older idea than Einstein's time-space, but I do believe that the ancient Egyptians and the people of antiquity had much different views than that. So with the other idea, so as you can see, as it is ascending, or you can make it descend, it doesn't matter either way, but as soon as this turns around, it's actually going to make an elliptical pattern. It's going to make an elliptical pattern. Okay, so let's put this stuff aside. And so let's go into the creation of the electromagnetic field. So if we take this pencil and we consider it the current, now as it's pushing through the ether, and we have the disruption of the ether, it is going to push those circular patterns, and it's going to wrap itself around the current. Now let's take a step back, I should say, and let's look at the pattern itself. Now as you can see, it's going to twist around, twist around, twist around, and it's going to come into some stable patterns. So as you would in school, so we're going to go to another part that's the beginning of a repeating pattern. So here you go. This is one full cycle of this pattern. And now we're going to get it into frequency. So I just have here in my notebook just the idea of frequency. So this particular pattern from start to finish is going to be one time. Now you can do this over and over and over, so the same pattern is going to repeat twice in the same amount of time, so that's going to be 2 times that frequency. Okay, so when we go back to the model, we're just going to take one complete cycle of this pattern. Okay, now that we're back to our rope sample here, so here starts the pattern, and here is one complete cycle of that pattern. Now remember in video 1 when we were talking about the resonance or the rebounding, so as this is going back and forth, it's going to rebound and circle around and make that backbone pattern. So that is the resonance. Now let's look at it from a top angle. Okay, so now from the top you're going to get these beautiful rosette patterns. So remember the rebounding. So this is going to be one cycle of this frequency. So if this was a sound wave, this would be its cymatic pattern. The cymatic pattern was a little bit more difficult to do with the double helix. So what I think I'm going to do is I'm going to look up some references and get you the top view or the cymatic pattern of a DNA. Let's get back to these ether disruption patterns and put them in a systems context. That's what I'm trying to say. Systems context. So, all right. So we'll ignore that for right now. But here is the top superior or north aspect, and this could be the south, inferior, whatever you would like to call it. But anyway, it is going to be the top and bottom of a toroid. So now, what is a toroid? Well, basically, it is a donut shape. So I have a couple of macaroni noodles here, and I'm just going to join them together for you. Now, this isn't perfect. It more or less looks like a heart, but trust me, it's supposed to look like a circle. So here we go. So it's going to just have a center here and around like that. When we break it apart, we can see the two aspects. So this is the north or the superior, the south or the inferior. Really doesn't matter, like I was saying before, because it depends on the angle that you're looking at it, or if you want to flip the system around, you can. It doesn't matter. The way that it's going to matter if we follow the current, which is going to go right through that. And then north and south aspects are going to matter, but this isn't going to matter for the moment. Okay, so now the north and south, remember that they are going to be pushing and pulling, squeezing and contracting. Remember that weeble wobble? So that is going to be the north-south aspect. And that's also going to be called the magnetic, because remember that current that's going to relax or reduce the pressure here, and it's going to push it towards each other, and then the inertia is going to make it spring open, the close and open. All right, so the next aspect of it is going to be almost like a shearing motion. It's going to go around this. So I have a pencil here, and I'm just going to demonstrate it a little bit. Just like this. I'm not sure if you can see that. My little diagram here. Please excuse all that. I just wanted to squeeze it in. It looks as bad as my regular notes. But anyway, so I have a pencil. It's going to represent that toroid or that macaroni noodle. So now I'm just going to wrap this red thread around it. That is going to be an east-west aspect of it. And it's basically just going to be a shearing motion, an east-west. So as you can see, it's just going around and around and around and around. All right, that's that. So this east-west aspect or the shearing is going to be the dielectric. Okay. So there's going to be multiple names for the magnetic and the dielectric. So the magnetic can be called the H field, and the dielectric can be called the E field. The most important aspect that you have to just keep in mind is the north and south. They're just going to interact like this. So say if you have multiples of these, they're going to be like this. And if you have the east-west element or the dielectric, they are going to be like this. They're going to interact like this. They're always going to be at a 90-degree angle of each other. So, and then the E field is the one that, say, in antenna work, that this, the one that's going to go like this, is going to be picked up by your antennas. Okay, so this picture represents a traditional way of looking at things. So basically, here is your current. In this picture, they're saying it's propagation direction here. Okay, so here is your magnetic wave or your H field. Here they're calling it your B field. Here is the electric field here. I was calling it the dielectric, and of course it's called the E field. So here are your sine waves. I'm just going to take it from here. So here's your sine wave, here's the other sine wave, and together they are going to make a sphere. All right, so it doesn't matter, say, if you do it this way. So if it's directly up and down, this way they're going this way, but if you just rotate this 90 degrees, it's going to be the exact same thing as what we had in the book. Let's explore one more disruption pattern of the ether. All right, so we have our current and our disruption patterns here, but let's just follow the top just for a moment. So we're following it along. It's going to, at first it's going to do the same thing like it did, but instead of shooting down here, it's going to shoot straight down. And as we progress here, it's going to go up, straight down, and now it's going to start to shoot in the opposite direction. So here is what it was going to do. So it's going to go loop around and come down. In this new pattern, it's going to go around, go straight down, and loop this way. So there's going to be equal and opposite push in either direction. Okay, so let's go to the bottom section. Bottom section is going to do the same thing. So it's going to make that same looping pattern, but instead of shooting up, we're going to go loop around and go straight up. Okay, let's follow this same as up here. So we're going to loop around, go straight up, and after it curves, it's going to pass the current again, and now it's going to shoot straight down. So here is a summary of that one. So the old way is just going to loop around and go straight up. This pattern is going to loop around, go straight up, down, and shoot. This is also going to have an equal and opposite pull, just like you're tying a knot. Okay, so let's zoom out a little bit. So here's the top pattern, and here is the bottom pattern. We're going to take those two new patterns and we're going to put them together. All right. So that's how they look like together. It's just going to look like a big old bow tie. So let's do it again. So let's do the top, which is the blue. So it's going to go around, down, and shoot up. The bottom is going to go around, up, and shoot down. What you're going to get is you're going to get the result. If you remove these two things, we are going to get a cardioid pattern with those two empty spaces here. All right, so now how mathematically can we get a cardioid pattern? Well, let's take this away. Sorry about that. All right, so this is a vortex pattern here. So what you're going to see here is that Volkswagen kind of symbol here, and then you're going to have some sacred numbers, the 3, 6, and 9. These are going to have a triangle pattern, but in this way we're just going to not use those sacred numbers, the 3, 6, and 9, and we are just going to use that Volkswagen kind of pattern. So that's the first way that you can get a cardioid pattern. The second way you might want to do it is through Fournier Transform, which basically is, remember that sine wave that we were doing earlier? You're just going to take that and then you're just going to wrap that into a circular system. And that's how they got this pattern here, but eventually, if you do it over and over and over again, it's eventually, now if you can see that, it's going to turn into a cardioid pattern. Okay, there's another way that you can get there, and this is my favorite way that you can get there as well. And this is coming from a modular math. So as you can see here, or maybe not so easily, there is a cardioid pattern right here. And what these little lines are is basically they are the angles of reflection of light. So this is actually the way that your eyes are going to see and how the light is going to go onto the retina. But anyway, let's focus on the cardioid pattern. This is a schematic from Vitruvius's 10 Books of Architecture. So what is this? It is an amphitheater. Okay, so before you say like, well, what does this have to do with anything? So as you see here, there is a 12-pointed star with all these letters. So let's make a cardioid out of this. So you see this L and the M. So what we're going to do is we're going to take the point of this and we're going to draw it here. And we're taking the L and we're going to draw it to this end of this semicircle. Okay, now we're going to take this K and we're going to take this and we're going to draw that to the end of this and this to the end of this. We're going to make a double stacked cardioid. So now that we have the cardioids down via this 12-pointed star, let's explore how the cardioids are related to harmonics or the proportionality. To do this, we have to go back to this system of this 12-pointed star. All right, so I believe in video 2, we had already went over some of these triangle patterns, which are equilateral triangles. So what do I mean by that? So let's go back to these diagrams via the golden ratio. So we have these angles of 120 degrees, but if you just connect those, we will get these triangles. Now you're going to remember these shapes right here. So remember this shape here and this shape here. And so the reality of this is that this is a 4 stack of equilateral triangles. So 4 of these stacked on top of one another. So let's explore that. And so in my poor artwork here, you can see I tried to do that right there. Okay, so because of the Fibonacci sequence, we have determined that this and this has a 2-to-1 proportion to it. Now let's grow it into that flower pattern. So we had determined that this little flower pattern in the middle is the first harmonic, and that the outer ones, these bigger points, are a representation of the second harmonic, the 2-to-1 ratio or proportion here. It's going to be the same thing here. So if you see this inner ring here is the first harmonic, and then the second one is going to be a representation of the second harmonic. It's not going to be any different than what we had already explored here. Okay, so now what does that mean? Well, it simply means that both of these sections are in certain proportions to the stage right here, this inner circle. Now let's take the theater part out of amphitheater. So now we just have the prefix amphi. So now what does that mean? So that just means of 2 sides. Now originally I thought it might be a word that says amplifying, but if you actually look at it, from a source, say if there's a performer here, the sound isn't going to be amplified up here. In fact, it's going to be the opposite of that. So as say if you're somebody that's sitting up here, you're going to get more air resistance. And so I suppose you could call that impedance. So it's not, these structures aren't actually for the amplification of anything, but it just means of 2 sides. And if you say of 2 sides of what, because that's a curious thing, just think about this. It's of 2 sides of a resonance, I should say, or a rebound. Or if you want to think about it in this terms, remember in that cardioid right here, this little heart shape, and here was the 2 empty spaces formed by our disruption patterns. So you could say it is 2 sides of that, which actually is 2 sides. And you can actually kind of see right here in our macaroni noodle, it would be 2 sides of a toroid. Now let's take a look to the stage or the platform in relation to the stands. All right, so we're just going to do this. So here's the stage, here are the stands, and you can see that there's one level here and one level here. So now the stage is set deeper, so not only that you can see the performer here, but it's also for proper sound distribution. And that's the whole point of the 12-pointed star. This is the maximum and equalized distribution of sound through these angles. We're going to get off topic just a little bit, but we're going to use the same diagram. So now that we know that these angles represent sound distribution, what else can we use these buildings for? Well, luckily for us, Vitruvius does give us a clue. And actually, the page previous, we just kind of got lucky, so we can just scooch this over just a little bit. And I don't know if you can see that wording here, but he does go over the 4 equilateral triangles, and it has to do with those points of the stars meeting that circle. So now there's 12 points on that circle, and the 12 points, or those 12 sections, do represent the 12 signs of the zodiac. So now, what does that really have to do with anything? All right, so now we're going to talk about very, very old ideas, but are still relevant today, and very large patterns. So now we're going to take a look at the Earth, and as you can see, it's spinning, and here's the line of our axis here. And as you can see here, it does have a little wibble wobble. So now I'm going to back it out just a little bit so you can see this. All right, so you can see that wibble wobble, and it's making a conical section here, kind of that hourglass here, as you can see. Well, not with my hand in the way, of course, but anyway, as the axis is going through that ellipse, what it's doing, this from end and back again, that is going to be about 26,000 years. Now we're going to split that up, and that each section of that 12 is about 2,100 years. This is called the precession, and those 12 sections are the sections of the zodiac. This is more or less a traditional view of the zodiac. Now it has to do more with astronomy than astrology, although we might get into a little astrotheology in a minute. So as you can see here, as it's going through its precession, I should say, here are the different symbols of the zodiac signs. Now, each one of these zodiacs are associated with a planet as well, but we're just going to take some star systems, and just in general, each one of these star systems is going to emit a certain frequency in proportion to our solar system, and especially to the Earth. All right, so I may or may not use this section, but if I do happen to squeeze it in, there are certain stars that mark the position in this precession here. So let's go into a different picture here. So as you saw, there's going to be certain stars that are called pole stars that help us know where we are in the Weeble Wobble. So we do have the constellations here, or the star systems, and so as each one of these star systems has its own unique frequency in proportion to our solar system, the sun, and the Earth. Now, each one of these star systems frequencies has its own set of characteristics. So because I was talking about the swastika in the last video, I think it's only fair to just do a little bit of the astrotheology and so how we get there. So, as we said, there's the Weeble Wobble, we have the pole stars, and now how do we determine if we are in a certain age? Well, according to the Weeble Wobble, if on the spring equinox, if So say we are in the age of Pisces now. So as the precession is going through, so on the spring equinox, if the sun is in front of this constellation, we know that we are changing our pole star. So that is how we know that we are entering a different age. So we are kind of right in here. We are ending Pisces and we are entering the age of Aquarius. Let's go over some of the characteristics of each of these star systems. All right, so let's start with Aquarius here, the age that we're entering. That is the age of truth-bearing, unveiling, structure, things of that nature. Now as we go backwards, here's Pisces. It is symbolized as fish. So this is an age of governance, kingship, control. And let's go back to, I apologize about that. So now we go into the age of Aries. Now because we're talking about the symbolism of the swastika and the modern propaganda of this, so you're going to see Aries, and of course this is where the term Aryans come from. Now the characteristics of this age is self-awareness or knowing. So the age of the age of Aries is the age of knowing. So if you're saying an Aryan, it's the ones who know. So it's not like a black and white thing as in skin color. So I wouldn't want you to think that Aryans is necessarily Nazis. It's not associated with a National Socialist Party. But Aryans, if perverted, the ones who know, so it, in a way, if you're talking about black and white, you're talking about people that are illuminated, and then you're talking about the illuminated ones keeping the rest of the people in the dark. Originally, this age is knowledge for everyone. So that's just all that I wanted to talk about Aries. We can go back into Taurus. That's more of like the age of like agriculture and things like that. But each one's kind of oppose and complement each other. So say the age of knowing and the age of truth bearing. And so like Taurus would be, like I said, it's egalitarianism versus the age of control, that kind of thing. So anyway, that's just a brief overview of that. Okay, so let's remember our amphitheater and our 12-pointed star. Our amphitheater was only half of that, remember? So, and then we have our sound distribution angles to these various systems. So what buildings like those amphitheaters and the coliseums and horse track races and other buildings like that, they can be used as astronomical clocks. Now this one is a famous one in Prague. It's probably the oldest one that at least I can think of. This one is at least about 600 years old. And what we're going to be doing is we're going to be talking about this little circle right there. And that, as you can see, these are the symbols of the different constellations. Later we will get into this little clock right here. But as you can see, these are just symbols of the 12 points of that star. This is going to be a traditional timekeeping clock of hours and, of course, the day. But we're going to tackle timekeeping in just a little bit. But for right now, we're just going to concentrate on big cycles. So here are some examples how the astronomical calendars work. So here is our symbols for our constellations here. And here is some symbolisms for the sun. They're actually dials on the real clock. And here, these represent the moons and the different stages of the moon as it rotates around the Earth. So now we have the new, I should say, first full and last quarter of the moon. So this is all a 28-day cycle. So as you can, maybe an example might be chimps, gorillas, and Homo sapiens, or human beings, our menstrual cycles are connected to the lunar cycles. So 28 days, and the cycle of the moon is about 28 days. Okay, so now another way to use this calendar is to determine seasons. So it's another heads up and what we can expect, like when to start growing our crops and other things like that. If you're a denning animal, and you don't really have to be a denning animal for this to happen. So right now we're entering the vernal equinox, which is the spring equinox. So days are getting longer. So when the days are getting longer, you're going to start producing more serotonin, and the more serotonin you're going to produce a whole concoction of things. You're going to produce more dopamine, more hormones, more sex hormones. The more sex hormones you have, the more sex drive you have. The more sex drive that you have, of course, equals into more babies. So as we enter the spring, it's baby season. And so what do we do to represent all the little ones that appear in the springtime? Well, of course, Easter and bunnies and chicks and such like that. Okay, so now that we have a little bit of an introduction, this thing is so very complicated, but it also does address eclipses and leap years, just as a FYI. But now we're going to switch from this astronomical calendar to something very familiar that we probably all use on an everyday basis. So let's address some of an ordinary timekeeping piece and how we got there. So to do that, let's go back to Vitruvius here. Let me just a second. So we're going to address the 12-pointed star and also the angles of that. So this 12-pointed star also can represent the 12 months of the year. So, but we're going to go into the actual circle itself and how it's relative to these angles and everything else that we're doing. All right, so when it comes to angles from the middle of a circle and out, there's a few ways. We all know that this is a 360 degrees, but let's go into the measurements of 1 minute of an arc. So you can divide these things into very, very small numbers. So what is a minute anyway? Well, a minute of an arc is 1/60th of a degree. So if this is 360, one little slice here. So 1 minute is 1/60th of that slice. Okay, so then what are you going to do? What is going to be smaller than that? Well, that's how you get seconds. So 1 second of an arc is 1/60th of 1 arc minute. So that you're going to take that one little slice of the arc minute and you're going to divide that into 60 angles as well. So what does that mean? It means that 1 second of an arc is 1/3600th of a degree, or 1/129,600 of a full 360 rotation. I don't know about you, but when I was in school and was being introduced to minutes and seconds, I pretty much glazed over it. But I'm glad that I do remember that it was mentioned, so I got a chance to go back to it. So anyway, so as you can see, the Greek system was very similar to the Egyptian system of telling time, especially during their day, and the Greeks just ended up doing it just with a little bit more sophistication. As if you would look at it from the top, the Egyptian way, you would see it as an ellipse, and in this way you're just seeing it as a circle. All right, so now that we have very, very small measurements, let's go to a very large measurement. So we can use a system called parsecs. So that is a very large way of measuring things through angles. So we can do that measuring going to star systems. So basically what it's going to be is, so let me use my notebook here. So as you can see, we're going to use some angles here, and I don't know if you can see my little diagram, but here is the sun and here is the earth. Now this is at the so say if you had both solstices, like maybe the summer and the winter up here, and so we know that they are 180 degrees apart. So let's take it at the 90 here. So here is going to be your star or your constellation system. So a parsec is going to be, you're going to measure the distance that it appears to move in comparison with the background. So that's what all that is. So say if it should be here and you think it's moved here, and here is your angles. So what we're going to do is, because this is going to be that 90 degree, because you don't actually know what that angle is, so you can't do that. So you have to take 90 minus whatever that angle is, and then you are going to find your different angles, because you already know that this is going to be a 90 degree angle. So in that way, you can actually, through the Pythagorean theorem, you can actually tell the distance between the sun, the star system, and the earth. Just think it's like a triangulation, like an ancient way of GPS. I guess that's a good way to say it. So think about like the Antikythera mechanism and all that stuff. Now you can actually put this, like say if that's the sun, earth, and the moon. So that would be that kind of system there. So basically what you can do is you can actually see where you are on the earth, and through the other mechanisms you can relatively tell when and where you are on your journey. So let's turn it this way and maybe you can see it just a little bit better. So you can see here, this is going to be the rotation here, and according to wherever your star system, you can actually tell where you are on that rotation. So now that we know that this can possibly measure distances and time through arc angles, what other functions can these buildings do? Well, let's go back to its original flow pattern. So all right, so here from the stage, say a speaker is speaking or acting or doing whatever they need to do. So now it's going to distribute that sound. All right, so the actor or the speaker is going to generate sound waves through his or her voice. And so that is going to take place through electromagnetic waves, and then from that it's going to emanate. So the speaker is going to do the same thing as the building. So the building itself is going to act as a speaker. So when you have a speaker, you'll need a receiver. So if this is one half, this can actually, this and the receiver can be known as antennas. Let's try to put some of these ideas together from the original flow pattern. So of course we're starting with our current. We do get our disruption patterns. So we have the top and the bottom, and joining that we got the cardioid shape. Now I want you to remember that cardioid shape there with the two empty spots there. So from there we progressed to Vitruvius's Amphitheater. So we had the first and the second harmonic, which were in proportion to the stage. All right. The distribution of sound, or the capture of the sound or electromagnetic waves, can make these into antennas. All right. And then when we get to antennas, we have to think about the dielectric, or the E field. And as you remember that, the E field is going to go around and round and round like that. That is going to be the mechanism of which it's going to travel in the air. All right. So let's go here. We're going to now, instead of a vertical plane, let's go to a horizontal plane. Now sometimes these are expressed in art through doorways. So here you can see the beautiful proportions here. These can be interpreted as octaves in the same tone in proportion to the stage area. So let's go through a few examples of these. So let me get myself out of the way here. So here we go. Here's a pedal pattern, and we saw that pedal pattern before in the harmonics. So let me just remind you of that. So we get these shapes here, and we also do get triangle shapes here. Here's the first harmonic and the second harmonic. We do see all that. Now you're going to see the occurrence of some nubby things right here. And I know that's not really a scientific word, but we're going to use it. So I don't know for sure, but to me, these look like resistors. Now, what does a resistor do? Well, they are going to, as the name suggests, it's going to resist, change the speed, I guess the speed, or change where a current goes. Okay, so here is that pedal pattern, the harmonics to a stage. And just keep in mind that there's whatever they're using this technology for is going to be progressed in the next picture. Okay, let me get myself out of the way again. Now I know this doesn't really show up very good, but here's that same pedal pattern here. There is the harmonics here with all the different proportions. Here's the little nubby things. And now we're going to couple the stage with a cymatic pattern. So here's a cymatic pattern here. Here's a triangle with the harmonics. There's antenna here and another cymatic pattern here. So I'm not sure if that's just coincidence that this point is matching this point, but like I said, however they're using this technology, I would really love to know how they're using it, because nobody makes all that stuff without a function. All right, so let's get on to get past that, and so let's look at some examples in real life, which is the whole point of the biology, right? All right, so let's go back to Vitruvius, and you're going to see in that original flow pattern, you're going to see the first harmonic here and the second harmonic there. Let's get back to that picture. So this is just the vertical. Let's go to the horizontal with the ear. We already went through the flow pattern. All right, and so here is going to be the most resistance here, and then going into the ear is where that H pattern is going to go. I'm sorry, not the H pattern, the E field. The H is going up and down, the E is going this way. All right, so now that we have the outside of the ear, this is just your typical drawing of your outer and inner ear. So that electromagnetic wave is going to come in, and now it's going to bump into that tympanic membrane here. It's going to vibrate back and forth. It's going to make these auditory ossicles, or the bones, they're going to hit and vibrate this whole structure here. Now these semicircular canals, they are oriented in 3 planes, so basically we can orient ourselves in space, so, or in our environment, I should say. These do have magnetic crystals in it, so that's what helps us do that. All right, so and then in this cochlea here, we've already been through that pattern with the Fibonacci, or the golden ratio sequence. So here again, and so this is going to be the sorry about that, I just cut myself in the middle of a thought. So I was going to say transformer, but I do believe the more correct one is a converter. So it's going to convert electromagnetic waves into electrical or neural signals. And then you can see the vestibulocochlear nerve here. So, and then that's going to go on to the brain for interpretation. Now, beyond the cardioid and the ear, where else can we see this pattern of these original flow patterns here? Well, let's get this to focus here. So you're going to see all these are in the embryonic stages. So if you take this just a step up, they're all going to form a neural tube, and then they're going to go into the original, or that flow pattern. So now you can see all these little C shapes here, and if you use a little bit of imagination, you can actually see that cardioid in each of them. All right, depending on what stage these are going to be, and if they've already hit the derm stages, which is the 3 layers. Oops. So the ectoderm, the mesoderm, and the ectoderm, which provides the conditions of different organs and functions. So depending on where the DNA is going to send the current, and the environment is going to determine the specialization of the tissue. Let's go back to the original cardioid. So what was that? That was basically a circle encircling a circle. So what happens if we do that twice? If we have that circle encircle that circle twice. All right. So this is from the Mathologer YouTube channel, and he is great. If you need any math systems explained, he's a really good one to do. So this is the modular, or he calls it the times tables within a circle. So let's just run this video, and then you can see the circle encircling the circle twice. All right, so this pattern here is called a nephroid. So now what is it? It is pretty much 2 back-to-back cardioids. So now where do we see this? If you got kidney from nephro or nepher, you are correct. So the circling of the circle twice is the shape of a kidney, or a kidney bean. All right, so now let's slice this in half and see what we get. Okay, that is the inside section of the kidney. Now, do you see anything familiar? Well, let's go back to that auditorium of Vitruvius. Now we can see the relationship of the sound distribution of the first harmonic here. So let's go back to the kidney. And that's no surprise and no coincidence, because this is going to emit a certain frequency. In fact, all the organs emit a certain frequency, and it's actually no surprise that the organs are called organs. And what's more is, I think it's a beautiful thing that all the organs have to be in harmony or in concert with all the other organs, and to make your body function the way it does. All right, so that is it for today. I'm sorry that this was so long-winded, but please join me the next time. We are going to tackle the king of it all, which is the creation of energy, and we are going to layer some toroids in a star formation. So I hope you join me then. All right, till then, stay magical, everyone, and we'll see you next time. Bye.